In this video, I'm going to go over an example that was motivated by this book by McElrath entitled Statistical Rethinking. And the whole idea is what we're going to try to do is estimate the proportion of the world's surface, portion of the Earth's surface that's covered by water. And to keep things simple, I'm going to assume that there's only 5 possible answers to the question, what proportion of the Earth's surface is covered by water? Either 60%, 65%, 70%, 75%, or 80%. What we have in this column is my prior belief. So I just made a guess about what proportion of the Earth's surface might be covered by water. And you can see that, in general, I'm thinking it's around 70 to 75%. So I'm saying that my prior belief is there's a 35% possibility that it might be 0.7. There's a 50% possibility that it might be 0.75. And there's only very tiny possibilities that it might be some of these other values. So now what I want to do is I want to come down below and I want to look at this table. And I want to look at the formula for Bayes' theorem. So this is probably the most important video of the entire workshop because it really focuses on this equation here, which is the essence of Bayes' theorem. And so you really need to deeply understand that formula. And to help with that, what I've got here in this table are a series of calculations that I'm hoping will make clear what this formula actually means. So let's look at this table. So we're going to start off with our values of theta. So these are the possible proportions of the Earth's surface covered by water. And then we've got the probability of theta. Got it in the table. And here we see it in the formula. And this reflects my prior beliefs. This is my prior. So there's a 5% chance that 60% of the world's surface is covered by water. A 35% chance in my prior beliefs that 70% is covered by water. These are nice little probabilities because they all add up to 1.00. So that's my prior. What's this thing? This thing is the likelihood function. And so remember, the whole idea about a likelihood function is that the parameter varies. In this case, the parameter is going to be theta. That's going to vary while the data remain constant. So what were the data that I collected? Well, what McElrath said was take a globe, toss it up in the air, grab it with one hand, look at where the right thumb sits, and decide on that whether the right thumb sat on water or land. So that's sort of what I did. Actually, I didn't do it with a plastic globe. I just used a random number generator, but same idea. But I actually did go through this process using simulation, and I got 4 out of 10. So effectively, I tossed the globe 10 times, and 4 times it came up on water. So those are my data. So if we think about the likelihood function, well, the likelihood function is going to be based on the binomial. And so, again, the idea is the data are constant, the parameters vary. So what we're going to have is 10 choose 4 theta, and that's going to vary, raised to the power of 4, because I got 4 waters, 1 minus theta, raised to the 6. So if we want to use a specific case, let's see, if we want to think about this guy right here, you'd have 10, choose 4, we've got This value here is 0.6 raised to the 4, 0.4 raised to the 6. And that would give us 0.1115. So, these are the likelihoods. Now, what I'm going to do is, I'm going to multiply the likelihood times the prior. So, there's my likelihood. It's going to be multiplied by the prior. When I do that, what's it going to give me? Well, it's going to give me the joint distribution. Because think about it. P theta times P data given theta is going to give me the joint of theta. Excuse me, that should be that should be a comma because it's the joint distribution. So the whole idea is, in order to get a particular combination of data and theta, first you've got to have a particular value of theta, and then you multiply that by the probability of data given theta. So each one of these numbers represents the joint probability of data, 4 to 10, and a particular value of theta. So that's our joint. So when you multiply this together, what we get is the joint. Probability of data and theta. Okay, I'm just going to take a moment and clean this up. Okay, so what happens next? So if this is our joint, what we've got at the bottom here, if we sum up all these joints, what we get is the probability of the data, which is equal to the probability of getting 4 waters when we do our experiment. And as I said earlier, there's a couple of ways to think about this. How do you get 4 waters? Well, there's 5 different possibilities. Either theta was equal to 0.6 and you got 4 waters, or theta was equal to 0.65 and you got 4 waters. Add that to theta is equal to 0.7 and 4 waters. Add it all together, you get the total probability of 4 waters. Or, as we saw earlier, if we think about trying to calculate the probability, the marginal probability of a tree being any one species, we start off with the probability, the joint probability, that a tree is in a particular species and height class, and then sum over all the height classes. So this is the probability of the data, this is the probability of the data. Now what we want to get is that last column. We want to get this last column, that is probability of theta given data. So what is the probability of theta given data? It's just the joint probability, data and theta, divided by the marginal probability of the data. And again, to see this, think about what happens if you multiply the probability of the data times the probability of theta given the data, you wind up with the joint probability. So what we're going to do is we're going to take each one of these joint probabilities, these are joint probabilities, we're going to divide it by the marginal probability of the data, and that's going to give us what we really want. The probability of the theta given the data. And this is our goal. This is the posterior. This is the posterior distribution. It was obtained by dividing the joint by the marginal. And it's kind of interesting to see what has happened here. Because I actually did the experiment and got 4 out of 10, which we can pretty much assume is not a terribly good estimate of what the true proportion of the water is on the Earth's surface. But what's happened here is that, even though this is a really bad estimate, when it comes to our ultimate conclusion, our ultimate conclusion is, hey, it looks like about 70% would be the most probable with a 42%, maybe a bit higher, 75 with 27%. But what's interesting that's happened is, although I had the data being an underestimate, the fact that I had these priors ultimately gave us an answer shown here in the posterior distribution, the thing that we are really concerned with, which actually was closer to the true value.